being a woman in physics myself, I've often been, one of the very few women in the classroom. And I've never seen any women's name in any of the textbooks that I ever studied in physics and astronomy. So to me, it was a lonely place to be.
Hello everyone, in this video we have an exciting conversation with Dr. Shohini Ghose. She has more than 20 years of experience in the field of quantum physics as a professor, advocate in diversity, and as an excellent science communicator. She's going to share her story in quantum from the time that she was a student, and we are going to talk to her about some of her projects, for example, her book in this conversation. By the end of the video, we're going to talk more about the future of quantum, and we're going to talk about how you can get involved in the field of quantum computing more actively. We hope you enjoyed this conversation. Hello, Dr. Shohini. Pleasure to have you.
Hi, nice to be here.
Yes. So Dr. Shohini is a professor in physics and computer science. She has been in the field of quantum computing for almost 20 years, right?
Oh my gosh, yeah.
Yeah.
Time flies.
Yeah, and she's a great science communicator and advocate in diversity. So we are pleased to have her today in QAI. She's also the Chief Technology Officer of QAI. And we are excited to hear her story in quantum, but also as a scientist. And we'll kind of talk about her books, her activities in science communication, and also maybe some of her experiments and quantum work. So maybe we can start with the first days of quantum. Like, how did you get the inspiration to work in this field, and how did it look like at those years?
Wow, so going back to my student days as an undergrad, there wasn't even really a field of quantum computing the way it is today. Of course, quantum mechanics existed and has been around for a long time. So I got to do an undergraduate research project on this one topic in quantum physics.
And when was that?
This was in the US. I was doing my undergraduate degree in physics and mathematics at Miami University in Ohio.
Okay.
And so I worked with this professor. He gave me this really interesting project on cavity QED, which is this quantum-focused project. I didn't really know what was cavity QED, but it was something that I, looked at the equations and could do some calculations and some coding, and got to calculate some new things that had never been done before, which was very exciting to me. And the professor I worked with, Perry Rice, he was very encouraging and supporting. And he said, hey, if this is something you like doing, you might think about these graduate programs. And one of the programs was at the University of New Mexico with a theory group that was just starting to develop research into this new thing called quantum information science.
And what year was that?
Oh my gosh, that was back in 1996.
1996.
Yeah.
Okay.
So I thought, hey, why not? And that was a pretty lucky place to be, because that's when things started growing in the field, and the idea of how to use all of the established theory in what's classical information theory, and use that language and that mathematics and framework and apply it to quantum mechanics to try to figure out, can you do information processing, things like computing or information security kinds of tasks, using the laws of quantum physics. And that seems fairly common now, but back then that was new. So we were even inventing language and trying to understand deeply what it all means. For me, it was really about just trying to understand the laws of the universe a bit better. I didn't really know this would become this huge, big area that is now, becoming commercialized, and there's a whole industry growing around it.
Right. And I guess at that time it was mostly theoretical, right?
Yes. So there was no actual existing quantum computer back then, although there were experiments. And some of the very first experiments were about trying to just control the individual states of atoms and trapped ions and so on. And of course, those became the platforms that now are being used by companies and by much bigger groups all around the world to try to explore large-scale quantum information processing.
Right.
So the experiments were there. They were just maybe at a smaller scale, and they were restricted to research. Now it's really more about actual application and trying to do tasks. Yeah.
And how did you choose the field that you are working right now? What was your inspiration? And I mean, for our audience, what is your research background right now?
So yeah, because I started in the early days, you're right, I focused in theory. I'm a theoretical physicist. And back in that time, I was working on just general questions about the foundations, I guess, of quantum theory, which is what are the things we understand well, and why is quantum physics so different from our everyday experience? So these days you hear, even in just media, you hear about entanglement and superposition. Everybody knows these words, right?
Yeah.
They've become almost like pop culture words.
Right.
But these are actual quantum phenomena, and they kind of describe these weird properties that atoms and photons and these sort of very micro scale particles have, which are very different. They're almost like superpowers compared to our world, where these entanglement can be connection across space and time in ways that we cannot imagine, things like this. So for me, that was really interesting. As in, why is it that atoms can be entangled, but people can't? So what's quantum about quantum, and why is there that boundary between quantum particles like atoms and us, although we're made of atoms? So for me, those were the questions I was starting to explore. And in the process of doing that, it became very much about trying to understand what do we mean by information itself, and how can we therefore use quantum ideas to control information. And that, of course, led to quantum computing. And for me, nowadays, I study things like building a quantum internet. Why? Not necessarily only because it would be really cool to have a quantum internet and do cool tasks, but because in the process of building something like that, or building a quantum computer, you actually learn more about what is entanglement and what is superposition, and what is that boundary between quantum and classical.
Right.
So that's kind of what I still do. And
Right.
really, I think I'll probably be exploring it my whole life because it's a hard problem and
Yes.
beyond our everyday experience.
Right.
So I think that's what really excites me and fascinates me.
So following on that, how would you explain quantum internet?
Wow. So we don't have a quantum internet today, but broadly what we mean by quantum internet is to create basically a network of communication, for example, things like what we already do, so security in our communications by sending information, but in a way where the security, for example, could be guaranteed using quantum ideas. So that would be a quantum internet where there's quantum encryption being used,
Right.
or quantum kinds of information being sent. In fact, we can even use different forms of transmission. There's this thing called quantum teleportation,
Right.
which always sounds sci-fi when I say it loud, but it's actually a real thing,
Right.
where you can actually teleport quantum information from one location to another. So that could become part of a quantum internet, or maybe different parties across large distances could be connected by sharing quantum entanglement, and that could allow them to do tasks in different ways, perhaps either to enhance security or privacy or efficiency in some way.
Right.
So it'll be like a layer on top of what we already have. It's not like we're going to somehow get rid of our current internet, because it's pretty good.
Right. Right.
And we're just trying to enhance it and try to identify what can we do better using
Right.
quantum.
So these ideas like quantum entanglement and quantum teleportation are super exciting. Maybe in another video we can explain them. But what do you think are the advantages of such a quantum internet? Is it about speed or safety? What is it about?
I mean, there are different possible kinds of advantages and benefits. I don't think there's just the one answer. It's about whatever tasks you're trying to do, right?
Right.
So perhaps you're trying to enhance security, then you would try to figure out what are the quantum resources, how do you entangle particles, how do you do measurement, and how do you transmit your data, things like this. So for different tasks, perhaps you're trying to build some kind of another layer of security for things like a blockchain, for example. Then you would want to think for that particular task, what resources would you use and what's the cost of that versus the benefits and things like this.
Right.
There could be other tasks where privacy is more important, anonymity might be important. Perhaps you're thinking about some voting protocol.
Right.
Where everybody has to remain anonymous.
Right.
And also where you have to guarantee people's identity and certify them.
Yeah, and quantum is good at that, right?
Yeah, depending on what resources you have, right? So good is kind of general. We have to think about what's the cost versus the benefit. So it turns out that it's actually quite difficult and costly to build things like a quantum entangled network. At some point, maybe in the future, it will become easier to do as we get better and better at engineering. And that's when that resource cost will come down and the advantages will go up. And that's kind of where all this R&D is going.
I see. Excellent. That's a very exciting project, Quantum
Right,
Internet. So I know you also have been teaching for a very long time at the university, but also to public. You have a famous TED Talk with millions of views, and you have been active in the community in teaching quantum. So can you share a little bit about your experience in teaching quantum, how it changed over time, what were the challenges, and what are the opportunities?
I think I'm very lucky to be able to teach something as amazing and also amazingly difficult to explain like quantum. So I think quantum is uniquely challenging to teach because it's outside of our everyday experience, right? So for example, if you want to teach a physics course perhaps on Newton's laws and forces and how things move, we can experience it. I can say, oh, here, look, this is, if I drop an object, you can see for yourself the effect of gravity, and then you can test it and feel it and measure it and things like this. So that's what I mean by experiencing it.
Right, physical.
Yes, physically and observing it. We're all actually experts on Newton's laws because we walk, we jump, we move, and all of that is actually Newton's laws in action. So the difference to quantum is that it's not really our macro world experience, right? When we talk about quantum theory, typically the effects like entanglement and superposition are at that individual atomic level, which we certainly cannot see. Or, I mean, we have things that we can touch and we are made of atoms and so on. But at the individual level, we're not really observing and experiencing things like superposition.
And does that make it difficult to teach or talk about?
Right. So this is why I think there's that added level of sort of separation from the theory itself. But on the flip side, it means that I'm always reminded of how powerful we are in being able to imagine things that are outside our experience. That is what it means to be a scientist, and creativity and imagination do play a big role.
And that's what it makes it exciting, right?
Absolutely.
And creative.
Yeah, how amazing that our tiny little human brain somehow can imagine these crazy sci-fi spaces of superposition of particles that exist. They may exist, they may not exist. We have all of these behaviors which we can write down very precisely with mathematics.
And we cannot even see,
No.
We cannot even see with the microscope with light, right?
Exactly.
Like when you get that down that size, you need like electrons to be able to see them, not even light.
Yeah, but on the other hand, we can see the consequences of those kinds of characteristics. So in fact, the reason we have quantum theory is because there were scientists, back over 100 years ago, who were able to observe interesting things about what we see when we observe light very carefully, all of the different colors and missing colors, and how different gases absorb and emit different types of radiation. By really carefully measuring all that, we could infer that there's this amazing hidden world of atoms and atomic structure and how photons behave as light and as a particle and wave at the same time. All of this we inferred from what we can actually observe,
Right.
and built this incredible huge theory, which of course is powerful, and we know that it's powerful because that theory led us to be able to describe every single element in the periodic table, for example.
Right.
So all particles, all matter in the universe came from this one amazing theory. So to me, that's powerful. And that to me is the way in for people who are first experiencing quantum, even though you can't really experience it. You can experience the excitement and wonder of creating a model, a story, which we can verify by looking at things like elements like hydrogen and helium and uranium and any element in the periodic table, and understand its properties and confirm the theory is working. Every time you see oxygen behave the way it is, or look at chemical reactions or new kinds of materials, all of that is a confirmation of quantum theory.
Right.
So in that sense, it is something that we're constantly engaging with, and it makes it real for students who might get a bit worried when they first hear the concepts. So there are many ways in, and I think we're surrounded by quantum because it is the fundamental theory.
Right,
So that's
right.
part of how you make it exciting and engaging, I think.
Amazing. So I can hear that you need a lot of creativity and maybe imagination
Yes.
and maybe understanding the theory, but someone who hasn't been in the quantum field, what do you think are the requirements for them to understand how they can get started?
Well, it depends, I guess, if you're talking about a degree. Is that what you mean? Or are you talking about even earlier? Or
Anything. Like I get a lot of questions from my friends who are software engineers, who are school students, family. Some people think it's so hard that they can't do it without a PhD, but I know it is doable, and with spending some time you can learn a lot. So what is your recommendation for people who want to know more about quantum, how they can get started?
Yeah, well, again, it depends on how far and how deep you want to go, right? Of
Right.
course, you can go all the way and get a PhD in physics if that's what you want to do. Absolutely, I think you should, but you don't have to. I agree with you. This new area of quantum computing actually lies at the intersection of physics and mathematics, chemistry, computer science. So there are many ways into this particular area, kind of like we think about regular computer science too, right? It's not like you have to get a PhD in computer science to use a laptop, right? Or do
Exactly.
some kind of new app. There are different ways to be part of computer engineering, computer science field. Same thing with quantum computing, where to get a start, really, it's about thinking, what is a task that you might want to solve? So a famous task in quantum computing is to try to factor large numbers.
Right.
That's a math problem, if you think about it. It has nothing to do really with physics or certainly not quantum mechanics. It's a math problem. Mathematicians love those kinds of puzzles. Computer scientists like it. Why? Because they want to build code to try to solve that math problem, but using computers. Now, quantum computer scientists would be people who would try to use quantum code to solve the factoring algorithm. In fact, Peter Shor famously did come up with this kind of an approach. So my point there is that you don't actually need to know all of quantum physics or physics in general. You need to know what are the rules for coding,
Right.
in order that where you can use things like superposition and entanglement. They're kind of like extra knobs, which means they're extra commands in your code or instructions that you would give a quantum computer, saying, okay, now use this type of superposition, or now build this entanglement and make the quantum bits, qubits, talk to each other in a particular way to solve a particular problem.
I see.
So without really knowing all of the physics of superposition and entanglement, you just need, oh yeah, these are extra buttons, right? They're sort of that, take your device and add in an extra power that will allow you to do your problem better.
I see.
So in that sense, to be able to use that kind of extra power, you do need to know a little bit of background, in terms of coding for quantum, but it doesn't take a lot. So you can take some training. A lot of the companies who are building quantum computers like IBM and Google, they will offer, some initial introductory courses, but you can also go to of course, universities that offer these kinds of programs. So there's lots of different resources now.
I see, I see. So I hear that there's a lot of resources, but if they know what specific problem they want to solve, they can try some solutions without the need to know all the physics or getting a degree.
Sure, exactly, yeah.
Okay, so here comes the exciting part that I'm very interested to talk about. You have your book here. It's called Her Space, Her Time. I'm gonna show it in this camera and in this camera. So it's a very interesting book. Can you share your, like maybe a brief summary of the book? What was your inspiration for writing it and your stories behind it?
Yeah, so I can tell you writing this book was just as hard as doing quantum computing and quantum physics and that PhD.
Then that might have been very exciting.
Yes. And in fact, you're right that writing, of course, has different aspects of creativity and imagination that you need for this. So this was actually my pandemic project that I sat down and wrote this. So pandemic, don't get me wrong, it was a very traumatizing time. It was not just a fun time writing, but to me it was almost like therapy writing this book. Amazing. But actually the book itself was much longer in the making. The name is Her Space, Her Time, which is referring to the many, many women who have actually contributed to some of the biggest discoveries in physics and astronomy, but we don't often hear their names. So a lot of people know names like Einstein and Newton and Schrödinger. I mean, there's lots of famous scientists. And if people are asked to name a woman in physics, they might name Marie Curie. But beyond that, it's not really something that people can easily name women's names. But the truth is that if you really start looking into the history of how all of these different discoveries happened, things like the Big Bang, or starting out the entire field of particle physics, or discovering dark matter, or a lot of the space program, making that all happen. Every single one of those kinds of discoveries and achievements have had women contributing in a big way. So being a woman in physics myself, I've often been, one of the very few women in the classroom. And I've never seen any women's name in any of the textbooks that I ever studied in physics and astronomy. So to me, it was a lonely place to be. And I think that's a problem, because then you start wondering, oh, maybe this is not for me. Do women really belong in this? Maybe men are better at it, because that's all you see around you, right? All of the people you hear about, the famous people, the textbooks, there's literally, women are deleted from it all entirely. So that was worrying to me. And so I started thinking about it as a scientist at some point. I said, okay, why is that, right? Let me think about it, find the data, figure out what is it that we do know about factors that drive women versus men to study physics or not, what are the skill sets, things like this. So I started looking at it as a research project, talked to researchers who actually know much more about these, have an expertise in gender studies and sociology and psychology, and started realizing there are many factors. Most of them are contextual and social, and sort of these roles that we have assigned to men versus women and things like this that have led us to these sort of differences. But in fact, turns out it's not true that women are not involved in all of these discoveries. So not only did I understand what is the context that leads to this, but I also started learning about all these women who have contributed. We just don't celebrate them in our textbooks. I thought, why shouldn't we, right? It's not like we have some limited number of pages where we must use for celebrating or not celebrating people, right? So why not include everybody in the story? So, over the years, I collected a lot of these stories, and I never really had a time to do anything with them until pandemic happened. I thought, okay, I just want to tell these stories, and writing about these women and their amazing achievements was, as I said, that therapy that reminded me of being inspired even in hard times.
And your story as well, right?
Oh my gosh, a little bit of my own experiences, because you're right that I wanted to link all these historical women's experiences to what it's like to be a woman in physics and astronomy today. So yeah, there's a little bit of my story in there too.
Amazing. So yeah, the book is called Her Space, Her Time. Yeah, you can buy it and have a look. It's a very interesting book, and I'm glad that we have you here to give us an intro to the book. But another area that you are doing a great job is science communication, and maybe we can get a break to have a look at your TED Talk. You have a well-known TED Talk in quantum, so we use the break to watch a TED Talk together. So getting back to your science communication experience, you have done a lot communicating quantum to people. And what are your thoughts, uh, how people in the scientific community can connect to people better, and what was your experience? Like, how did you develop that? What was the exciting part of working with people, especially in quantum?
Yeah, I think it's really, really important for us to get outside of this bubble of people we talk to, on the technical side about quantum, my fellow scientists, my research team, and really bring it to the broader audiences, because in the end, this knowledge is for everyone, right? As I said, this is the foundational question of how does our universe work, and what is our place in the universe? And so that big question is for everybody to engage with, not to mention now with quantum computing and quantum security, this quantum internet we discussed. This is all becoming more relevant even beyond just this foundational knowledge piece. This is relevant about what we're going to use, what tools will be available. So people should have a good understanding of technology going forward. It's very much like with AI, right? We talk a lot about how we, as a society, how should we use AI? What's good? What's bad? How do we benefit and not inadvertently cause damage at the same time?
Right.
So because of all that, this is a conversation that cannot just be done by scientists alone, right?
Mm-hmm.
This needs the community to engage with it. So that's why I think this science communication is really important, but it has special challenges in quantum just because, as I said, quantum, it's not really explainable using our everyday language because it is outside of our experiences. Right. So we have to be a little more creative in talking about the impact of it. What does it really help us in terms of how we use it, but also what's exciting about it, what's deep about it. So over the years, to answer your question of how I've engaged with it, I've certainly learned a lot. Some things I've learned to improve. Some things just don't work. You don't really want to go into too much detail if not needed. So I think great science communication is when you can relate the topic at hand to whatever is the interest of the audience, and connect at the level where everybody can find a way into the topic.
Mm-hmm.
So, for example, in quantum computing, one way, and I think that is really broadly accessible, is to think about something like, healthcare. Everybody wants to, engage with that as a topic. But the way it connects to quantum is that we might potentially be able to develop, for example, better kinds of drugs for treating diseases that we can't treat right now, if we can better be able to simulate the molecules and structure at the molecular level of these drugs. Right. And to do that, quantum computers might be interesting and important. Mm-hmm. So even without understanding the detail of quantum, I think the relevance and the importance of that in healthcare, exactly, is one way in, and a way to draw in different audiences. Not to mention, we need healthcare experts to tell us what is the actual missing piece or the problem that's super challenging to address. So the healthcare professionals have to talk to the quantum computing professionals. So that's another type of science communication that needs to happen. It's not just always just for broad general audience. Right. It's for different audiences with different expertises and different kinds of interests.
And based on what I see, the quantum field also needs that, like people from different sectors, like healthcare, chemistry, finance, coming, using the systems, and telling the quantum community like what they need.
Yeah.
Because you're very much at the beginning and you're just figuring out like where is the application. So there's like real benefit to that. But when you were sharing your science communication story, you were talking about the power of involving people in this.
Yeah.
And did you have any interesting feedback about people's concerns or questions about how these technologies are being used, about the ethics of it?
Yeah, I think that's a really important part of it, and often in my talks and presentations, I will always build that in because I don't think we can really separate the science from the people and the society and those impacts. So often you will see the standard science talk is only about the science.
Right.
And I don't think that's actually good science communication, because only talking about the science is only taking part of why it's important. So you're right that often people are more interested in the impact of it. What are, should we use it, shouldn't we use it? We talked already about these questions for AI. And back in the early days when AI was being rolled out, people weren't asking those questions. Then we realized, oh, there are all these, unexpected bad kinds of potential uses of AI, and now we have to be careful. And there's this whole field called quantum ethics. I mean, AI ethics. Yeah. We need quantum ethics similarly. So I think that those are questions that people are asking more and more. I find it really interesting that people do actually come back with questions around, why should I kind of care about it? As in, it feels like it's far away, right? If you just talk about quantum. But the answer to why should I care kind of question usually is about connecting it directly to something that does matter to them. So my response to that would be to first ask them, what is it that you do care about, as in what are your interests, and then let's see whether there is something there that we can build on.
Yeah, and maybe another angle to that is sometimes we miss is that a lot of quantum is already here. Like these cameras we are using,
exactly.
This video should use a lot of quantum principles to be able to function. Our computers are using quantum, and in the energy sector we have used quantum physics. So it's never too early to think about ethics, regulations, and policies. You don't have to wait for ChatGPT of AI to start thinking of it. Well, that's a very interesting conversation. It's maybe something we can go deeper in another talk and conversation. But I mean, you have worked on a lot of things like advocacy about diversity, teaching, science communication, and technical work. But now you're CTO of QAI, and can you explain what was that transition for you? What was the reason behind that? How do you see the industry, and what are your aspirations and motivations to work at Quantum Algorithm Institute?
Yeah, so coming into this role as CTO at QAI was yet another new challenge for me, and I guess I am somebody who likes to explore new kinds of horizons. And QAI for me was a unique opportunity because you're right. I've worked both on the technical side, but also trying to engage with different audiences and to think about communicating what this field is all about, and also the societal impact, which is around who is controlling the technology, who gets to use it, who is the future generation of quantum scientists. Are we including everybody fairly and equally and ethically? So these are questions that I've been exploring anyway in my work so far. And QAI is that opportunity to kind of combine all those areas, because the mandate for QAI as a government-funded institute here in BC is to take what is in the lab and in all this research and bring it out of the lab, and think about how we can connect all the science to society and explore all of the different potential uses of this technology, and also think about how to do it in a way that is most beneficial to society. So to me, that is exactly what is my interest. And so this role gives me that chance to work both with scientists and researchers, as well as people from industry, people from government, think about broadening the future workforce and also the potential users of this technology. And that's all about people and society. And that combination of thinking about the science as well as the people is what is where I want to be. And that's what QAI is working in. So to me, that's really important.
Amazing. That's a great perspective. And maybe last question, how do you see the quantum field going in general and also specifically with your personal experience as a CTO of QAI, as a science communicator, and as an advocate for diversity?
Yeah, so predicting the future is always hard, right? I say that nobody should. If you think even about regular computers
Right.
back when they were being developed, nobody could really have ever imagined. If you were somebody from the 60s, I'm not sure you could predict, unless you were one of the writers of Star Trek, in the sci-fi shows, you would see these handheld devices, people talking to it, and it looked wild because it was supposed to be fiction.
Yeah.
So back then, what was fiction is now reality. We have these handheld devices, and they're way more powerful than what you saw in Star Trek. So I think that sort of amazing, surprising evolution of technology is something that is always unpredictable. And I think quantum computing is probably the same. We are in the early days still, although now we do have actual working prototype quantum devices, quantum computers. And in fact, if somebody wants to try to learn more about quantum computing, you can actually go online, create an account with, let's say, IBM or D-Wave or these other companies that have these prototype machines and try it out for yourself. So these are not going to be the kinds of devices that are going to be very useful for real world, large scale kinds of tasks, but they're great for testing and learning and benchmarking. And that's where we are already today. And it's way faster than people would have predicted. So when I was a graduate student in the field, as I said, it didn't even exist as a field at all. And now we have working quantum processors. So what's going to happen in the next 5 to 10 years? Who knows? It's going to be fast. It's going to be exciting. We can't predict it. We should all be talking about it for sure and understanding where we want to go. Because as you mentioned, quantum has already impacted our lives, transformed it. And that's not how we talk about it. So things like the transistor and all of our electronics wouldn't have existed without understanding how matter behaves and how light behaves and how the periodic table properties are all, have certain patterns and why silicon behaves the way it is, which is why we can make things like transistors and integrated circuits and so on. All of that was quantum, and that to me is actually a great example of bad science communication because quantum scientists never called it quantum.
Right.
Right? So we don't engage with quantum in a familiar way because we never thought of the last decades of technology that we've been developing as quantum. So let's not do that going forward. I do want to expand this conversation, which is kind of why we're doing these kinds of chats, to bring people into the conversation and really talk about quantum in ways that all of society can be engaged and involved. And maybe that will help us shape where the technology goes and how we use it. For now, we don't know, but definitely quantum computers are coming in a big way. And it's going to be up to us whether it's going to help society or harm society. And I'm voting for let's help society.
Amazing. So I hear we have an exciting future and there's a lot of work to be done.
Yeah.
And we are here to work with people, industries, and companies to make that
Absolutely.
great future.
Come join us.
Yeah. Thank you so much. It was great to have you. And yeah, looking forward to work together. And thank you for the conversation.
Thank you, and I should mention that it's a great pleasure for me to have you working with us here at QAI as well, with your own technical background, and maybe you should say something about what your goals are and why you're in the field too.
Well, I have very similar line of thinking. Like maybe that's why I'm here, and that's why we're working together. I think there's a lot of exciting solutions and applications we can bring through quantum. There are a lot of problems that we can solve to help our societies, our industries be more prosperous, more efficient. But we also have to be careful how we are doing it. So we need to engage people, universities, industries, and we really need to work together. Like quantum has been a very collaborative field from the beginning. It's a group effort, and it's a tough thing to build and solve. So we need involvement from different parties to be able to successful and make good products out of it. And yeah, that's how I see it, and I think that's why I'm here, and that's why I'm interested in the learning and solutions part.
Great. I think we're on the same page.
Yes.
Great. Looking forward to working together.
Yes. Thank you so much.
Thank you.